In this video, we'll compare and contrast two different scoping rules, lexical and dynamic scope. So recall that scope determines where a given binding is considered valid, that is to say, where a name can be used to refer to its value. And the nesting of scopes will control the lookup of free variables. So if we want to find the value of free variable, we have to start searching the local scope, and then it's the enclosing scope, and then the enclosing scope, all the way down the list of all the nested scopes until we eventually reach the primitive scope. So the scoping rules of some language determine the order of the nesting of those contours or of those scopes. So as I said, we're going to consider the main two types of scoping rules, lexical scope and dynamic scope. So lexical scoping, otherwise known as static scoping, is the sort of normal scoping rules that we're already used to. This is what Scheme uses when we're talking about these nesting of functions. So in lexical scoping, the environment nesting matches the nesting of the code structure itself. So if we have a function defined inside some other function, then the scope of that inner function will be described or depicted inside the scope of that outer function. Okay, so what this means is the scope of a function can be determined at compile time and will remain static throughout all of execution. So if a function is declared in the global scope, it will always be nested in that global scope. Right. So this is used in a lot of common languages, like all of the Algol family languages, Haskell, and all the C family languages, etc., including Scheme. Though it is worth mentioning, the C family has restrictions where nested functions can't be declared, so we have essentially what's known as a flat scope, where all frames essentially get attached to the global scope. But it's very similar to this lexical scoping still, because it still matches the structure of the code. So Scheme was the first Lisp dialect to actually use lexical scoping. Prior to this, Lisp dialects used what was known as dynamic scoping, where lookup is done chronologically down the call stack. So first you consider the local scope, but if you don't find the variable there, then you look into the method that the function that called the current function. If that didn't happen, if that doesn't contain the variable, then you go into its calling function and its calling function, etc., all the way down the list. So the meaning of a variable binding needs to be determined at runtime because it's dependent or according to the most recently called function. Okay, so the different orders of function calls will result in different values of free variables. Now this is used in older Lisp variants. It's also, you can create dynamic scopes in Perl as well as lexical scopes there. It's also used in a lot of command lines because it happens to be an easier type of scope to implement. Okay, so between the two, if you want to consider the difference between lexical scope and dynamic scope, or static scope and dynamic scope, the simplest way to remember this is if you recall the dynamic and static chains when we were talking about activation records. So lexical scope, as we learned, means that we want to follow the static chain in order to find the parent scope. So if I don't find a variable in the current activation record, I'll go down to the static link, I'll follow that to the parent scope and look into that activation record. If that doesn't contain it, then I'll follow that static link into the next activation record on down the list. With dynamic scope, it means we're following the dynamic chain for variable lookup. So recall the dynamic chain is essentially when this function returns, I'm going to go back to that other function. I'm going to follow the dynamic chain to find out what the previous calling function was. When we have dynamic scope, we're actually using that dynamic link or that dynamic chain in order to find the meaning of free variables. So go to the function that called this one. If it doesn't have it, then go to the function that called that one, etc., etc. So dynamic scope can be nice. It adds some flexibility when we're dealing with functions. So for example, if you want to mutate the behavior of a called function without passing any extra arguments, you can just override one of its free variables before calling it. No need to edit the function itself. Okay. So languages that have exception handling, so modern languages essentially, they all use dynamic scope in order to implement this exception handling. So if an exception is thrown, then we have to essentially trace the execution back to the enclosing try block. If that one doesn't have a proper catch for the type of exception that occurred, then we'll go to the block that called that and to the block that called that, the enclosing try blocks all the way down. Eventually reaching the most recent catch block that can handle the existing exception. But there's a bunch of disadvantages when dealing with dynamic scope as well. It's harder to understand. It's a source of many more errors because you have these functions dependent not just on what you can see in the code itself, but also how that code gets used. And it's a lot harder for the compiler to optimize because, again, all this information needs to be determined at runtime, so it can't predetermine the values of how these variables will be, how these free variables will be associated with values until the actual function calls have occurred. So let's see an example to really concrete the difference between lexical and dynamic scoping. All right, so in this code here, most of it's all just one big function called a that takes a parameter x. Inside a, though, we have two other functions, b and c, which don't take any parameters at all. C happens first, so a calls c. C says define a local x and then call b. And then b says set some non-local x, some free variable x, to the value 2. So the question is, what x are we talking about here when we're setting this x to 2? So let's walk through this with lexical scoping. Let's say the nesting of all of these functions should match the nesting of our scopes. And let's see what that looks like in our contour model. So on line 1, we define a function called a, so we get a binding from a to the lambda on line 1 declared in the global environment. Everything else here is all inside a, so we jump down to line 9, which says run the function a with the value 1. So we get a contour for a that has the parameter x bound to the argument 1, and now we're on line 2 inside that new scope. Now on line 2 it says define b to be the lambda on line 2, so we get the lambda on line 2, and notice this was declared inside the function a, so our parent pointer refers to the scope for a prime. Okay, so that's lambda on line 2 declared here, and then we jump down to line 4, which does a similar thing for c. So we get a binding between c and the lambda on line 4, also declared inside a. All right, that jumps us down to line 7. On line 7 it says execute the function c. So apply this function to no parameters, or to no arguments rather, which is useful because it takes no parameters, so that works out well. So the body for c starts on line 5, so we get a contour, c prime, with no arguments bound to any parameters, so no frame here, and we're starting on line 5. When c is done, we'll return to line 7 because there's still more work to do in a. We have to do line 8 here. And when that's done, we'll return to line 9. Okay, so on line 5 it says define x to be 0. So define always creates essentially a local binding, a binding in the current scope. So we get x bound to 0, and then we'll move on to line 6. On line 6 it says call the function b. So we jump over to b. B takes, again, no parameters, so we get a contour for b. Now with b, it says set x to be 2. Now notice the contour for b was created next to c because both of them were declared inside a. So we follow this pointer, and this is the scope in which we create those contours. So we get c and b next to each other, essentially as siblings, which matches what we see in the code as well. B is next to c. They shouldn't be able to see each other's variables because they're essentially at the same level. By contrast, they both should be able to see this variable x, and you can see that they will, roughly speaking. If they look for a free variable called x, it'll be in this a. Now, unfortunately, c has declared a local variable x, so it hides that free variable. So it's not actually possible. This x here is not visible inside c because we've hidden it, but it still does have an enclosing scope. Okay, so if we're in b, we're on line 3. Line 3 says set x to be 2. So if we're in this scope here, inside this contour, we say set the value of x to be 2. We don't find x locally, so we go looking into the enclosing scope, and we find it in a. So we change this variable here to the value 2. Okay, and that's it for b. B is now done. It can now return, so this contour will disappear. And that's also the end of c as well, so that can get gobbled up and garbage collected, and we'll end up back on line, the end of line 7, beginning of line 8 in a. Okay, so b finishes, c is done, so now we're here, and that just says return the value of x. So the value of x is 2, so we'll return that, and we'll define result as whatever came out, which is 2. The result is 2. So with lexical scoping, it's a bit of an odd function, but hopefully easy to follow along because there's nothing really new happening here. But let's consider what happens when we use dynamic scoping. So I'm going to jump ahead a little bit here with dynamic scoping because up until this point, everything's the same. So what's happened so far? We defined a, we called a, then we defined b and c. So we have all of those. So we have x bound to 1 because we passed that in. We have b and c bound to the lambdas on line 2 and 4, just like before. And then on line 7, we call c. C creates a contour, so we have a contour for c. That defines variable x, so we have x bound to 0 inside here as well. Now we're at the beginning of line 6, and this is where the difference occurs. So we have a function c calling a sibling function b, right? So if I look in C, I don't find the name b, so I go into the enclosing scope, and there it is called b. So I run this function. But now when I run this function in dynamic scoping, I have to create the contour for it inside the current scope, right? Because the parent scope of the new function needs to be the most recently called function. So when we create a new contour for dynamic scoping, we create those contours inside the current scope. That's kind of what already happened up to this point, right? We were in the global scope when we called A, so we created the contour inside the global scope. We were inside A when we called C, so we created a contour for C. It just so happens that also matches these pointers, but we're kind of ignoring these pointers in dynamic scoping and just going with where we currently are running the code. That's where the scope gets created. So if we're inside C, and we on line 6 here, we call the function B, that's going to create a contour for B inside C. So notice C now goes around this contour for B rather than being beside it. So now if we're on line 3 in B and it says set x to be 2, we don't find an x locally, so we go looking into the enclosing scope. Now because dynamic scope has changed the rules a little bit, the enclosing scope is now C. So x here gets changed to 2. So instead of changing A like we did in dynamic or in lexical scoping, now we change the x inside C. All right, so that was here. We set x to be 2 from inside B. So because B was because B was called by C, the contour for B is created inside C. So the free variables of B also include the variables inside C. All right, so then from there we've mutated the value, and that's the end of B. So it gets gobbled up, garbage collected, and C also gets garbage collected. So it returns the value of B, this call to B, which doesn't do anything, and then we come down to line 8 here and return the value of x. So if we close all this, the value of x at this point is still 1, because the set changed this local variable, which has now been thrown away because it was never used. So this instance of x still refers to the x in A, which is unchanged, and the value ends up being 1. So with lexical scoping, we got 2 because B changed its parent variable. In dynamic scoping, we got 1 because this variable wasn't changed. When we changed the variable from B, we got the variable inside C because that was the most recent function call that had a binding for a symbol x. So with lexical scoping, the nesting of scopes matches the structure of the code. With dynamic scoping, the nesting of scopes matches the calling order. So essentially the call stack, if you will. All right, that's pretty much that example. So let's, I want to go back to this example here as well. So here's another example. It does pretty much the same thing. So we have a parent function, and inside that we have two sibling functions, if you want to call them that, f and g, which are declared beside each other. So using lexical scope, f shouldn't be able to see inside g and vice versa. But using dynamic scoping, because f calls g and g calls f, they have access to each other's inner variables. So just to walk through the contours for this, we have in lexical scoping, let's see where this starts off. Main calls f, then f calls g, and then g calls f. So main calls f, we have a scope for f. F calls g, so we get a scope for g. G calls f, f calls g. So because those are declared inside main next to each other, then the contours get executed or created next to each other. Now this recursion runs on forever, so just dot, dot, dot. Okay. Now with dynamic scoping, using the exact same code, because f is calling g and g is calling f, those contours get created within each other. So main calls f, and then f calls g, and then g calls f, and then f calls g, so we ended up with nesting of scopes. So a similar idea, walk through this one manually, see if you can't construct the contour models for it on your own, and then match them to the existing contours in the notes to make sure that you understand the difference between lexical and dynamic scoping. All right, that's it for this video. In the next video, we'll go looking at some other stuff that we can do now that we've added assignment into our language. Specifically, we'll talk about how we can implement object-oriented programming in this somewhat functional language.